Welcome back to Perturbation Theory and Asymptotic Methods. I had promised a few lectures ago that we would do a case study with some science in it, some application of the methods that we've been learning. And so, as promised, that's what we're doing today. And then we will move on next time to a new set of techniques that go by the name of Wkb theory. And so that'll be another little section of the course. But anyway, so today, as I say, I want to do an applied problem. It comes from biochemistry. And I just learned a little about it this morning while preparing the lecture. Let me show you some of the things I discovered. Okay. So the example I thought we could do is something that comes from biochemistry. It's very classic. It's called the Michaelis-Menten model. And it arises in biochemistry, or nowadays you would speak of systems biology. The issue is to think about certain biochemical reactions that involve enzymes and to understand something about the rate of production of the products of those reactions. So you can read about this in any book on mathematical biology. I would recommend this one by Jim Murray, Mathematical Biology, very noticeable with the leopard on the cover. Jim Murray's a great guy and a great mathematical biologist. Still alive, he retired some years ago. He's taught at Oxford for a long time, also at University of Washington, now lives in Princeton. Anyway, so his book is terrific and he gives a good discussion. But the thing that I didn't know, despite having heard about this model for my whole career in mathematical biology, is that Menten was a woman. There she is. It's from 1912 or so, this work that she did with Leonora Michaelis. I'll put something in our, I'll send you a link. I actually tweeted about it this morning, a link about the backstory of their work from the early 1900s. Very pioneering study in mathematical biology. Each of them had problems of their own kind. Michaelis, because he was Jewish, it was hard for him to get hired. Similarly, Menten had even harder problems in her career. She didn't become a full professor till she was 70, a year before she retired. Kind of ridiculous, considering the pioneering work that she did. But anyway, fortunately, we remember her great stuff. So let me now tell you a little what they did. So here's the setup. We're thinking about biochemical reaction involving a substrate. So think of that as just some molecule or concentration of molecules. And then I'm going to add an enzyme that will allow a reaction to take place. So the enzyme catalyzes this reaction, makes it happen faster than it would otherwise. And in the course of that, there's a complex that's made where the enzyme is the enzyme might be some protein, it's latched onto this substrate molecule. They make a complex together, and having done its job, the enzyme can be released, and you get the product of this reaction, P, and the enzyme is dislodged and now free to go about its business to catalyze more reactions. So these steps happen at different rates. This one we'll say happens at a rate K1. It can also go backwards. So you can go back from the complex, can unbind to make the substrate plus the enzyme again. So that would often be written as K sub -1, but the book that I was copying from this morning wrote it as K2. So I'll write it like that. That's the back reaction rate. And then there's a rate K3 of the formation of the product, like that. So I don't know, it's been a while since I took chemistry. I don't know if you remember your chemical kinetics. It may be a while for you too. But anyway, this is the standard way of writing such a thing. I'm going to write, I really should write something like S with brackets around it to mean the concentration of the substrate. And we're interested in tracking this as a function of time. But I don't feel like writing all those brackets. So I'll just call it S. So that is, I'm not going to distinguish between the name of the molecule and its concentration. Similarly, E would represent the concentration of the enzyme. And C will be for the complex, the enzyme substrate complex. And P, these are all supposed to be capital letters. P is whatever the product of this reaction is. I'm phrasing it very abstractly with enzymes and products. And I mean, it's not a chemistry course or a biology course, so I don't know if you're that interested, but enzymes do a lot of things. They can cut DNA, they can twist it, they can move electrons around in reactions. They're involved in say, attaching into hemoglobin molecules for, getting oxygen to your cells through the bloodstream. Enzymes do a lot of different jobs in cells and in the body. So we're just speaking very generically here. Okay, anyway, so let's now write down the rate equations that correspond to this picture that I put above. So the usual approximation that you make in chemistry in this circumstance is to ignore space. You think of the whole thing happening in a beaker that's all very well stirred up. So there's thorough mixing of everything, meaning that like the reaction rate for substrate to be colliding with the enzyme, that those collisions are occurring at rates proportional to their concentration. There's no spatial structure at all. And so you can write down the so-called law of max action for this kinetics, which would look like this. Say for the rate of change of the substrate. I mean, think about how can substrate change? Well, we can lose substrate because it's colliding with enzyme to make complex. So that causes a depletion of the substrate at a rate that we would write as minus K1, the rate constant, times the concentration of S times the concentration of E, right? That it's proportional to each of their concentrations separately. You could think of this probabilistically if you want to think of it that way, that the probability of an S banging into an E is proportional to how much of each of them there is. That's all. And similarly, we can create some S through this back reaction, right, going this way. So that occurs at a rate K2 times however much C there was. So the creation of S depends on the current level of C, and so we get a term plus K2C. Does everyone understand the reasoning for how I would write down these differential equations? You want to ask anything? Okay, so I'm going to just write down the rest of them. That kind of thinking leads us to equations then for the rate of change of the enzyme concentration, dE dt. We have three different things that can happen. We can lose enzyme because it gets made into complex. That happens at this rate. We can gain enzyme. Excuse me. We can gain it. Can gain enzyme through the complex coming apart to restore enzyme. That's up here. That happens K2C, creates enzyme. And we can also go this other direction to release enzyme by going to the right. Right, that can generate enzyme from complex. So that happens at rate K3. All right, so that's that equation for rate of change of enzyme concentration. With this kind of thinking, then I'll just write the others without going through each little step. dC dt is K1 SE minus K2C minus K3C. And finally, the product, capital P, gets formed at a rate K3C, where that's because the only way we can get product, by the way, this last reaction is irreversible. It only goes this direction. So the only way we make product is from C, from the complex. Okay, so there's a little system of 4 coupled ordinary differential equations. It's a quadratic system, right? We've got quadratic nonlinear terms like SE. Otherwise, it's linear, but there's a bunch of these SE terms. So, you know, if you were following it in phase space, you'd need 4 variables, SE, C, and P. But it's going to turn out that we can reduce this to a much lower dimensional system. We don't need 4 variables, really. For one thing, you might, if you're alert, see that these 2 equations are the same, except one is the negative of the other. All right, look at them. They're the same equation on the right-hand side, same terms. And so what this tells us instantly is, well, I mean, dE dt is the negative of dC dt. And so that means that if I take d dt of the sum of those 2, E plus C, that's 0. And so E plus C is conserved. Right, that's a constant for all time. Now, that should make biochemical sense because we're not creating or destroying the enzyme. The total amount of enzyme in the system stays constant for all time. It's either in the form of free enzyme or it's attached to the substrate to make a complex. And that's it. Okay, so I mean, there's just whatever total amount of initial enzyme there is. Some of it goes into the complex and some of it remains free. So this is going to equal whatever the initial amount of enzyme was. And we assume initially that there's no complex. We start the system with just substrate molecules plus enzyme. So the other initial conditions are, so let's see, initially there's some amount of enzyme, there's some amount of substrate. We don't imagine that there's any complex initially, and there's also no product initially. Okay, so that's our system. Now, by the way, this little equation that I just noticed, the conservation law, maybe I should just highlight this for a second. This means that we can immediately eliminate one of those 2 variables because their sum is a constant. So if I know how one of them behaves in time, I know how the other behaves in time by subtraction. So we will take the point of view that I guess we're going to eliminate E in favor of C. If we want, we can eliminate E of T from the dynamics. So now we're down to 3-dimensional dynamics. Since the E of T is just given algebraically by E0 minus C of t. So if I can figure out C of t, I will know E. Okay, so we now have sort of three dynamical degrees of freedom. And at this point, I guess I'm ready to introduce the main assumption. Is there any questions so far? Okay, so the usual, the reason we're doing this in the context of boundary layer theory and perturbation theory is that we're going to analyze this problem by making use of a very natural small parameter that arises in this system, which is that in a lot of circumstances in biology, there would not be much enzyme compared to the amount of substrate that it's acting on. So if we assume that the initial concentration of enzyme is tiny compared to the amount of stuff that it's going to catalyze, that will lead to a small parameter that we can exploit to analyze things. And this is what Michaelis and Menten did. They work under the assumption that the problem will simplify, and it still stays pretty realistic. We'll say more about that later. So the problem simplifies a lot if we assume that E0, the initial concentration of enzyme, is very small compared to S0, the concentration of substrate initially, as is often the case in real life, though not always. But we'll assume it's the case for our analysis here.
Can I ask a question?
Sure.
Does the system have any kind of conserved quantity that would correspond to like conservation of mass of the chemical reaction?
Oh, yeah. Sure, definitely. Right. So we had that conservation law that we just noticed about enzyme, but I think, you could add everything. If you add all four equations, that should be zero. The total concentration of everything should be constant because nothing's destroyed. Things are just interconverted. And you can see that if you just add the four equations, right? All the right-hand sides, everything cancels out. I think should be the case, right? Nothing's created out of, am I wrong about that?
You need
Doesn't
like
quite.
of 1/2.
Doesn't quite work, does it?
Somewhere.
What the heck?
I think it's because when you take the substrate and enzyme and combine them, you're taking two particles and combining them into one, right? So unless you associate the product with a higher mass state, you're probably
That's
not
right.
getting a concentration
Okay,
of mass.
wait a second. So I think I better change my answer.
Yeah, so I think it's not enough to just consider concentrations. We'd also need to know the masses of the chemicals involved, maybe.
Yes, I screwed that up. Really, so that's interesting. The right-hand sides don't add up to zero. Okay, interesting. Those first two, the second and third do have the same right-hand side, but yes, you're right. Okay, interesting. I feel like I thought I noticed some other conserved quantity though. Yeah, there's another conserved quantity. Look, if I did these two equations and add, no, that's not working. Wait, these two have the same right-hand side almost, except this one has a K3C, but I could cancel that out with this. So I should be at, what is it then? If I do something like, is it that S equals E plus P or something like that? Wait, we should be able to see this.
Yeah, I think that does.
Something like that, right? What is it now? If I go if I took the negative of ds dt and added that to dE dt, then the first two terms in each of them would cancel. I would be left with a plus K3C, so I could then go minus D capital P dt. That would be zero also, isn't it? I think I did that right. So that seems to be telling me that S plus P equals E or something, plus, or I don't know. Maybe we should just say it like this: E minus S minus P is whatever their initial values were. And okay, so that's another conservation law, I think, unless I did something wrong. Yeah. Does that look okay? We won't be making any use of that one, but yeah. Is that tantamount to conservation of mass? Sort of weird. I don't know. It seems like that I did that right, unless I've botched something up. But anyway, let me move along rather than getting embroiled. Was there another question, or are we good to go? Yeah, okay. All right. So anyway, I want to make this assumption about E0 much less than S0. And so we're going to introduce a small parameter. Let's let E0 over S0 be epsilon, and we're going to think of it as small. Okay. So what next? Now, what is it we're trying to do after all? I mean, one thing we could do is just try to solve the differential equations under these assumptions, but there is actually a biochemical point that people care about in that field, which is that they are often interested in an effective production rate of the product. They'd like to know how fast is the product being created. Like, can you eliminate these intermediate reactions and just sort of understand an input-output relationship between substrate and product? So the goal, you could say, is we'd like to have an effective rate law for the production of P. The product P. I'd like to understand the rate at which it's being produced. So, find a simple formula for that. For dP dt in terms of known rate constants and the various Ks. And maybe the initial amount of substrate or something, which should be readily measurable. Okay, so, and that's what we're going to get. I mean, that's one of the things that Michaelis and Menten figured out, how to derive such a simple formula from this system. And it's used all the time nowadays in systems biology and biochemistry. Okay, so to start analyzing this, it's helpful to, there's a lot of constants running around and various quantities with dimensions, units on them. So let us scale the problem. This is often what we do before applying perturbation theory. So we're going to non-dimensionalize the system. Let me first just, I'll first non-dimensionalize the concentrations, then I'll do the time. I'll take two steps in this process. In other words, like, what are natural concentration scales and what are the natural time scales? So one that's kind of obvious is I'm going to define a dimensionless substrate concentration to be, I'm trying to draw two different S's. This is a lowercase s in terms of the uppercase S, which was the original dimensional variable, divided by its initial concentration. So measure S as a fraction of its initial amount. That seems like a plausible thing. So then this S variable will be between 0 and 1 as a function of time. And you could sort of think of it this way. I mean, initially there's no product. So what is the natural scale for the product? Well, the only reason there's any product is because we started with substrate that gets converted into product. So a reasonable scaling for the product would be to say P is whatever the product concentration is at a given time, divided by the raw material that gave rise to that product, the S0. So we'll use that as the scale for the product. Whereas for the complex, I mean, the only reason we ever get complex or enzyme is because there was some initial amount of enzyme. There was no complex to begin with. So we're going to set the scale for the enzyme and the complex using the enzyme concentration initially. So those will be my dimensionless variables, and all of them will actually be between 0 and 1. Actually, I started with some initial S, so, well, that's safe. I'll say less than or equal to. All right, so anyway, those look like reasonable scalings, and now we have to do a bunch of algebra to clean up the rate equation. So let's see. Let's do the first one, d dt of S. So S we're now calling S0 times lowercase s. And the rate equation, if I go back, let me just stare at it for a second. Okay, so I'm working on this equation right now. I'm just going to substitute for the capital S and the capital C on both sides of this. So we have S0 times, well, there's a rate constant minus K1. S0 little s, E0 little e, then plus a term K2, and then that was times what? K2 times C, that's this. So in C we decided was little c times E0. So I have E0 little c here. And I'll just, same kind of reasoning, I'll do the other equation. D dt of the complex, so E0C is K1 S0 E0 little s little e minus K2 and then E0 little c and minus K3 E0 little c. Okay, so nothing sophisticated, just substituting. Now, by the way, in terms of these little variables, maybe I should make one remark, which is, earlier I mentioned that E of t plus C of t was always equal to E0. That was one of our conservation laws. So that becomes now, when I divide by E0, becomes this very pretty thing that little e plus little c is 1. So I can eliminate little e in places like this and that. The reason I'm doing that is I see that if I do that, I have a two-dimensional system for just S and C. They determine their own evolution. So that's nice. So canceling some stuff out, let's see here. I don't know. Maybe I'll just, rather than make a mess, I'll just go down to the next line. But you can see you can cancel out various constants like this S0. I can divide out with that. I can put it underneath this E0 if I want. Anyway, doing that kind of step, because our goal is to just isolate d dt of this dimensionless quantity S, little s. So we get d little s dt is minus k1 E0 S, then replacing the little e, I'll call it 1 minus c, plus k2 E0 over S0, little c. That's the first equation. And the second one becomes d c dt is k1 S0. I'm going to put a sort of a, I don't know, a parentheses around these things, which are just dimensional quantities. And then times stuff like S times 1 minus C. And these two terms are kind of interesting right here. These are both, the only variable in them is the little c. And they both involve this factor E0. And so the K2 and the K3 just combine. They add up. So this makes minus a K2 plus a K3 times C, where I've lost the E0 because I can divide out this E0 with this E0, this one, and that one. Okay, so now you can look at some units here. I mean, the S and the C are dimensionless, so you can read off that this has units of 1 over time. Right, because this side is something which is a dimensionless numerator and time in the denominator. So it suggests a natural time scale for the system. You could either think of 1 over this quantity as a natural time scale or 1 over this quantity. Those are both reasonable time scales. And actually, it's sort of interesting, isn't it? If you look at these two time scales, this one, this one or this one, if you look at the ratio of those two time scales, that ratio is epsilon. Right? Remember, epsilon is that ratio of enzyme initially to substrate initially. So it instantly shows us that there's very widely separated timescales in this problem. The two natural timescales in the system have a ratio of epsilon. So one is much faster than the other. Okay, so we have to make some choice. It doesn't really matter. I mean, if we choose one way, we'll be sort of working with the outer system very naturally, the outer region. And if we do the other, we'll be working with the inner in terms of boundary layer thinking. So let's just choose one of them. Let's choose this one that I've indicated to define a time scale. So to do that, I'm going to introduce a dimensionless time. Excuse me. Let's now let a dimensionless time tau equal K1 E0, that thing above that I said had units of 1 over time, times the variable time. Okay. All right, so there's my dimensionless time. And okay, so now we're going to rewrite the differential equations in terms of that. And we get, well, I mean, the easiest way to think about it is just think of the differential d tau as being k1 E0 dt. And every place you see a dt, just replace it by the corresponding expression with a d tau. So if you do that, you'll get let's see, I got ds over d tau. I mean, that's the first one. That should look very nice. I mean, the way I guess I want to think of it is take this expression, whoops. Take this thing that I've just indicated here and imagine sliding it underneath to conspire with the dt to make the whole thing dimensionless. Then you get ds over d tau. You get rid of that constant. So now you have minus s times 1 minus c. And then when we divide this expression by k1 E0, that'll cancel out this E0 with that one. So we end up getting plus k2 over k1 S0, the E0s have canceled out, all of that junk times c. So the whole thing is dimensionless now, and that big expression that I've introduced here, I'm going to call this lambda. It's some dimensionless group of rate constants and the initial substrate concentration. So I'm defining a new dimensionless parameter, lambda equals k2 over k1 S0. Okay, so in those terms, ds by d tau is minus s 1 minus c plus lambda c. Okay, meanwhile, I still haven't rewritten the other equation, the dc dt equation, this one. So same thing, we substitute in for time in terms of tau, and skipping some steps, here's what you would get. If you do the algebra, you get dc by d tau, a prefactor of 1 over epsilon, which should not surprise us. We made the time scale in the first equation 1, so this next time scale should be off by a factor of epsilon, and it is. And then it comes out to be s times 1 minus c minus another group, dimensionless group, which I'll call mu, times c, where if you work out the algebra, I mean, you're going to end up having to work on this expression. You will have divided by something with this in it. Anyway, it ends up coming out to be, plus you have to account for the epsilon to make the epsilon be outside of the whole bracket. So it ends up that this quantity mu, this other dimensionless quantity, mu is k2 plus k3, that's some of the rate constants that we saw earlier, divided by k1 S0. Okay. So that's that. Okay, so there's my system. Maybe this deserves to have some kind of, well, I think I'm gonna, okay, I'm debating whether to adorn it with something. I kind of like putting doodads around my equations. This is a good stopping point for taking a breath. There's my nice dimensionless system. And also we've got initial conditions on it. Let's remember what those are. The biochemically natural initial conditions are, remember we said S0, initially the substrate had concentration S0, but we've scaled things now by S0. So we're going to have the little s at time 0 is 1. Right, this corresponds to big S at time 0 is S0. And there was no complex initially, so complex at time 0 is 0. So those are our initial conditions. Okay, is there any question at this stage? We're now sort of set up to do phase plane analysis, or however we want to deal with this little second order nonlinear dynamical system. We talked a little about phase plane analysis in the last lecture, so it sort of works nicely for us to use it again in this context. All right, maybe before we move on though to the phase plane, I should remember one of our main goal here was to understand the rate of production of the product. So we ought to put that in dimensionless form too. Let's just do that first. Also, let's recall in dimensional terms, we had dP dt was K3C. So after we non-dimensionalize it, then this is going to give us K1 E0 d of S0p d tau equals K3 times E0 lowercase c. And so we can cancel out these E0s and swing the other constants over to the other side. And so this tells us that the rate of production dP d tau is, let's see, K3 over K1 S0 times lowercase c. Now, this combination of new constants, K3 over K1 S0, it's not actually new constants. If you look at the mu and the lambda, look at these two. If I subtract lambda, look at the numerator. That has a K2. This has a K2 plus a K3. Otherwise, they have the same denominator. So if I subtract, if I do mu minus lambda, I actually get this expression I have here. So this all equals, excuse me, mu minus lambda c. All right, so that's my production equation for the product there. Okay. All right, but anyway, notice the mathematical structure of what's happening. We've got this little self-contained universe of S and C, right? To see how S changes, I only need to know S and C at a current time. And likewise, to know how C changes, I only need to know S and C. The S and C variables have decoupled from everything else. They're their own little two-dimensional universe. Whereas P, the rate of change of P depends on C. So the information from C feeds into P. So P is driven by C. You could say it like that. But the dynamical engine driving the whole problem is the S and C subsystem. So that's what we want to understand. How does that behave? Okay, so now let's go into the phase plane and think about this. I'll look at our system again. We've got let's do the phase plane analysis on so we'll copy down this thing that's in the blue cloud. So let's say S prime, I don't know. So ds d tau, just to save writing, I'll call it prime. S prime is minus S 1 minus C plus lambda C, and C prime is 1 over epsilon S minus, or S1 minus C minus mu C. Okay, so stare at that for a second, and let's draw the plane. Maybe I'll put it because other books that I got this from a book. Actually, it wasn't Jim Murray's book; it was a different book. But they put C on this axis, so I'll do that too. And S will be on this axis. Let's suppose S equals 1 is here. I don't know, C equals 1. How about there? And so we want to try to understand the flow in this space. Of course, the S and C are positive or they're not negative, they're concentrations. How do you draw something like this, the vector field? A key to it is to focus on this equation right here. To look at this right-hand side. I mean, you've got to be worried about the 1 over epsilon. As epsilon is going to 0, that term looks like it's trying to become infinitely large, the 1 over epsilon. And that's true if this term in brackets is not 0, or even better yet, if this term in brackets is not order epsilon. Like if this term in here is some order 1 quantity, then this is going to be blowing up as epsilon goes to 0. So let's, just for the sake of discussion, let's think about what happens. Or actually, let's focus our attention on when the bracket is 0. So let's examine the curve. Where this thing in brackets is 0. So what is that? That's, if I solve it, I'd be writing S 1 minus C minus mu C equals 0, which I can solve. Let me solve it for S in terms of C. I end up getting S equals mu C over 1 minus C. Which has a vertical asymptote, you see, at C equals 1. For C near the origin, behaves like mu C. So behaves like a straight line. And it curves up. I don't want to get too close to the asymptote because that's not of any great interest to us. But I mean, this thing just keeps going up. In fact, it can go up to unphysical values of S greater than 1. We're not interested in what happens up there. But anyway, that's the basic idea of that curve. Now, why am I harping on that curve, the bracket where the bracket is 0? Well, because watch what happens if you're somewhere off the curve. And this is the interesting point. Or even for that matter, let's just think about what would happen if we started our initial condition, which is right here. Right, the initial condition is no complex and S equals 1. So what does the vector field S prime C prime tell us? Well, okay, I mean, let's look at what happens when S is 1 in this equation. So that term is 1. C is 0 initially. So this whole thing is just 1 right here. 1 times 1. And C is 0, so this term is gone. So the whole bracket is just 1 when I'm at this point. And then I have 1 times 1 over epsilon. So this is, like, is an enormous positive number. So when you start at this point, you have an enormous positive component to your vector field going that way. Now, what about S prime, the other term? What about the vertical component of the vector field? Well, these are all order 1 quantities, S and C. And let's suppose that the lambda and the mu are order 1. I didn't say that, but let's just assume that lambda and mu are nothing special. They're just order 1 relative to epsilon going to 0. They're just some moderate numbers. So with those assumptions, this S prime is order 1, whereas this term is order 1 over epsilon. And that means, and by the way, that is going to persist everywhere except in the epsilon neighborhood of this curve. Like if you imagine a little epsilon ribbon around this curve, then things might change. But away from a ribbon of thickness epsilon around the curve, where if this were epsilon, this could compensate for this 1 over epsilon. But away from that epsilon neighborhood of the curve, you have a gigantic sideways vector field. So I'll put a bunch of arrows on this. This is very fast. So what happens is you start at this point, and like a bolt of lightning, you just zap right into the epsilon neighborhood of this blue curve. And once you get within that epsilon neighborhood, then you have to start thinking again. And actually, when you're on the blue curve, what happens? Well, on the blue curve, this term is 0. So that tells you that C prime is 0, which means you're actually moving vertically through this curve, and you can actually show that you're going downward. You could check. You can see S prime, if I plug in a point on this curve, I have a downward order 1 component to S prime. We could check that, but I don't want to get lost in the sauce. This is what you're supposed to be thinking. What's going to happen is, oops, I didn't mean to do that. Starting here, you go zap on a very fast time scale of time 1 over epsilon, it turns out. Oh, sorry, time of order epsilon. This is the inner solution. Zap. There's an inner layer, a boundary layer starting near the boundary at time 0, an initial layer, we should call it. So you zap right onto this curve. And after that, you basically hug the curve. You stay within this epsilon strip and just slowly march down all the way to here. And the reason is, if you ever got off of this curve, like suppose you were over here, we could check that the wind is blowing equally strongly from the right over here. Again, horizontally. So you can't really get away from this little, what I'm calling epsilon strip around this curve. So a typical trajectory is going to look like this. Bang. And then just, you can't really even see the difference because epsilon is so small. Just going to slowly march down here. Slow meaning it's not, doesn't take time epsilon anymore. And that will take time order 1 to make any of those motions. I don't mean super slow, but order 1 time compared to order epsilon time. So order 1 over epsilon speed. So that's the basic geometry of what's happening in this problem. And so for this reason, this blue curve is called the slow manifold. You might wonder why you use such a fancy word as manifold. In higher dimensional problems, this would be a surface of some kind or even higher dimensional space. So it's a manifold. But here in this relatively trivial problem, it's just a curve. But it's, it's a smooth curve. So it's a manifold itself. Anyway, so we got this slow manifold, and after a short time, the system is confined to it. And so if we look at this equation in that light, this relationship that holds on the slow manifold is what people in biochemistry would call the quasi-steady-state approximation. The quasi-steady-state approximation is that S and C are linked by this formula. Except for the very short transient that we saw at the, during the bolt of lightning, S and C are just given algebraically through this relationship. If I know S, I know C, and vice versa. In our terms, in perturbation theory terms, this is the outer solution. So let's now derive it, just although it's pretty easy, with boundary layer theory, to see that it really is the outer solution to this problem in a boundary layer sense, which is why we're talking about it now in this part of the course. Incidentally, why would anyone call it the quasi-steady-state approximation? It's because for people who haven't done a course in perturbation theory, the way they justify it is they think of just setting dc by d tau approximately 0. If you sort of say that the system is always kind of in steady state in the sense that c is not changing in time, it's kind of like saying you're in a steady state, but it's slowly evolving. That's why it's a quasi-steady state. So if you're sort of always instantaneously in equilibrium in that sense, then you can derive the slow manifold, but that's not really the right way to think of it. You really should think of it as this boundary layer phenomenon where this is the outer solution that holds after a short time. Anyway, so let's just see that. How does that really work? I don't know. I mean, I guess we could, what's the good way to do this? I mean, I guess the way I would think of it is if I, it's so clear actually from the phase plane point of view. Maybe what I'll do is look at the inner solution, because that part is the slightly more mysterious part. Not much, though. Let me just look at what's happening in the inner region. Meaning the initial layer. Let's think about that, actually. So, in there, everything's happening on this very short time scale. Given that the speeds are order 1 over epsilon, you're moving a distance of order 1 in a time epsilon, right? By distance equals rate times time. So it seems natural to define an inner time scale, let's call it capital T, to be this dimensionless time tau divided by epsilon. That's sort of analogous to our usual big X, equals little x over epsilon in a boundary layer. That we've been doing for the past several lectures. So if we do that, and then rewrite our system in terms of that time, then you'll end up getting that these are the equations. dc by d big T comes out to be S times 1 minus C minus mu C, and ds by d big T comes out to be epsilon times minus S 1 minus C plus lambda C. So what's happening there? All that's really happening is it's really the same equations as above, as we're looking at here, except that whereas the epsilon appeared in this equation as a 1 over epsilon, it's now going to appear as an epsilon in front of that equation. That's really the only thing that changed. But so what's the interpretation? If I now start doing perturbation theory on this inner solution, and I write something like C of t equals C0 of t plus epsilon C1 of t plus et cetera, and similarly do S of t is S0 of t plus epsilon S1 of t plus et cetera. Right, try that. And we can go to lowest order. That gives us as much as we need. So just focusing on the lowest order terms, then you would get d C0 dt. Actually, before I write that down, I should record what are my initial conditions. In the inner layer, which is when I'm here, and all of this part, the initial condition is right there. It's that S at time 0 is 1. So I have S of 0 is 1, C of 0 is 0. So this is going to translate at lowest order to C0 of 0 is 0, and S0 of 0 is 1. Okay, so that's my initial condition. Now, the lowest order perturbation equations are here. Well, I'm copying from this. So taking it to lowest order, I would get S0, 1 minus C0 minus mu C0. And the other equation, though, this is a nice one. What is this to order 1? The lowest order of this is ds by dt is 0. It has no order 1 term. So that's just ds0 by dt is just 0. These are my lowest order dynamics at order 1. That's what we get. So this one, of course, tells you that S0 as a function of time is just a constant. And we know what that constant is because at time 0, it's 1. So it's just 1. So what this tells me is that S0 as a function of the inner variable, capital T, is just identically 1. And that's no surprise. That was my lightning bolt argument, right? This thing is just shooting straight across, staying horizontal the whole time. So to lowest order, that's what's happening. But the other equation, now I get to substitute S identically equal to 1, and that lets me calculate C. This gives me dC0 d big T is 1 times 1 minus C0 minus mu C0. So this becomes 1 minus 1 plus mu C0, and I have the initial condition. C0 of 0 is 0. So that's a little linear differential equation for C0, and we're getting the usual exponential decay away from the boundary layer. We just get exponential decay of C0 towards a constant. It gives us, if you solve it, you'll get C0 of T is 1 minus e to the minus 1 plus mu capital T all over 1 plus mu, for what it's worth. It's actually not worth much. I mean, yes, okay, so we get this exponential decay of C towards a constant. It tells us that C0 as T goes to infinity, so as we go out of the layer, this will equal 1 over 1 plus mu. We can calculate, and we would need that for matching onto the outer solution. But actually, I can tell you what happens. This point, 1 over 1 plus mu, is just simply this point right here. It's right where that horizontal line bangs into the slow manifold. To lowest order, that's what we're getting. That point is 1 over 1 plus mu. You can calculate that, but you'll see it's true. Comma 1. Get that out of the way. Yeah. So no big surprise from this. I mean, the perturbation analysis is not super interesting. The phase plane gives you everything that you could want. But here's finally the important point as far as Michaelis and Menten are concerned, that since we said we wanted to know the rate of production of the product, we now have that by using this steady state assumption that, essentially for all times of interest, except for the transient, on the slow manifold, which is where the system really lives for all observable times of interest, then we get this nice result, which is that S0 just obeys, well, however you want to write it. C0 is asymptotic to S0 over mu plus S0. That's one way of writing the slow manifold. And so you can take that relationship and plug it into the eliminate the C from the S0 equation, and you'll get d S0, d, the original time tau, is minus, I'm skipping a lot of algebra, but comes out to be minus mu minus lambda S0 over mu plus S0. And this is also equal to minus the rate of change of the product. And so this thing that I've just written down is what people call the Michaelis-Menten approximation, or the Michaelis-Menten effective rate law, which they derived in 1912. The Michaelis-Menten kinetics. So, I mean, notice what it's saying. The thing to keep your eye on here is this functional form, that the rate of change of S, how fast is the substrate getting degraded, getting consumed? It's being consumed at a rate that functionally goes like S over a constant plus S. That's the interesting function, S over mu plus S. Right, that's an interesting shape. That has a shape qualitatively like this. Whoops. If I draw S0 over mu plus S0, it's something that looks like this. It saturates. And so that's a very characteristic way that chemical kinetics behave in these enzyme catalyzed reactions. So you'll see this all throughout systems biology and biochemistry. And like I say, it comes out of this boundary layer way of thinking. Okay, so that's as far as I wanted to get today. I'll take any questions if you have any. All right, so that's, at least one example of where boundary layer theory meets science, but we could be doing countless examples from fluid dynamics or physics or you name it. But I think with that, I'm going to leave boundary layer theory for a while. We'll come back and do some more boundary layer problems later in the course, but I think it's time to move on to the Wkb method, which comes up in quantum mechanics and is really clever and interesting. And so we'll start doing that next time. Okay, I'll see you then.